So definition: suppose equals to E, an automorphism sigma of E is said to be F automorphism if sigma is fixed all elements of F, that is sigma of A is equals to A for all A belongs to F. So G of E over F. So this is important one. G of E over F is equals to sigma belongs to automorphism of E. So sigma belongs to automorphism of E. Sigma of A is equals to A for all A belongs to E. So this is a very important. So G of E over F is equals to, so sigma belongs to automorphism of F. Sigma of A is equals to A for all A belongs to E. Then G of E over F becomes group under composition of mappings, and it is called so F automorphism of E. So this is a group under composition mapping. So this is a group under composition mapping. So this is called F automorphism of E. So G of E over F. So G of E over F is equals to sigma belongs to automorphism of E, such that sigma of A is equals to A for all A belongs to E. So this is a group under composition mapping. So this is a group under composition mapping. This is called F automorphism of E. So next definition: a finite normal extension of E is called a Galois extension of F. So every finite normal extension is Galois extension. The next definition: so let f of x belongs to f of x and E is splitting field of f of x, then E is a finite normal extension of F. We can call G of E over F the Galois group of f of x over f. So this is Galois group of f of x over f. So G of E over f is the Galois group of f of x over f. Next one. Automorphism of E. So write E of H. EH is equals to A belongs to E. Sigma of A is equals to A for all sigma belongs to H. So A belongs to E. Sigma of A is equals to A for all sigma belongs to H. So EH is called fixed field of H. So this is EH is nothing but fixed field of H, where H is a subgroup of automorphisms of E. So this is subgroup of automorphisms of E. So next, this is note point. Let S be a fixed subgroup of E. Then, so degree of E over F is equals to degree of E over H. EH is equals to order of H. So this is note point. Next, so let E be a finite extension of F. Then E is normal extension of F if and only. So order of G of E over F is equals to, so order of E over F or index of E over F. Okay. So this is note point. So next to this. So this is important theorem, fundamental theorem of Galois theory. So this is very important theorem. So you can verify all previous papers. This question must be state and prove fundamental theorem of Galois theory. Okay. So theorem, fundamental theorem of Galois theory. So statement: let E be a Galois extension of F. So E be a Galois extension of F. So let K be any subfield of E containing F. Then the mapping K to G of E over K set up a 1-1 correspondency from the set of subfield of E containing F to the subfield of E over F, such that, so we have to prove these 5 conditions. So K is equals to E G of E over K. The first one, for any subgroup H of G of E over F is equal G of E over F. So H is equals to G of E over EH. So H is fixed. So next third one. So index of E over K is equals to order of G over K, comma. So index of K over F is equals to index of G of E over K in G of E over F. This is third one. So next fourth one. K is normal extension of F if and only if G of E over K is normal subgroup of G of E over F. Last condition. If K is normal extension of F, the G of K over F is isomorphic to G of E over F divided by G of E over K. So this is the statement. So statement for fundamental theorem of Galois theory. So proof. So we need the following result. We need the following result. The first one is finite separable extension of field F and let H is less than G of E over F. Then so G of E over EH is equals to H. This is the first result. So E be a finite separable extension of field F and let H is less than G of E over F. Then G of E over EH is equals to H. So next second condition. Let E be a finite separable extension of a field F. Then the following are equivalent. The first one is a fixed field of G of E over F. Second one, F is fixed field of G of E over F. Third one, index of E over F equals to so order of G of E over F. So these are the two results. So given that proof, given that E is a Galois extension of a field F, then E is finite and normal separable extension of F. So we know that every finite extension is normal and separable extensions. So every finite extension is normal and separable extension. Let K be any subfield of E containing F. Let S be the, so our assumption, let S be the set of all subfield of E containing F and H be the set of all subgroups of G of E over F. So we are defining a map. So define a mapping F function S to H. F function S to H. So S is nothing but S is the set of all subgroups of subfield of E. So we are defining a map F function S to H. So S is the set of all subfield of E and H is nothing but H is the set of all subgroups. H is the set of all subgroups and S is the set of all subfield of E. So we are defining a mapping subfield to subgroups, set of all subgroups of E to set of all subfield of E. So we are defining mapping F function S to S. So this is defined by F of K is equals to G of E over F. So the mapping is F function S to H is defined by F of K is equals to G of E over F. So first we have to show that this mapping is 1, 1 and onto. We have to verify defined mapping is 1, 1 function and onto function. So F function S to is defined by F of K is equals to G of E over K. So let K and L be the two elements of S such that F of K equals to F of L. So this one. So K and comma L. So these are the two elements. So our assumption F of K is equals to F of L. So we have to show that L is equals to K or K is equals to L. So this is 1, 1 condition. F of X is equals to F of Y, that is equals to X is equals to Y. So then we can say that F is 1, 1 function. So we are taking here in place of X comma Y, we are taking K comma L. So K comma L are any two elements in S such that F of K is equals to F of L. So that implies, so by the definition, this. So but F of K is equals to, so G of E over K. So f of k is equals to g of e over k, that is equals to f of L. So in place of k, we have substitute L. F of L is equals to g of e over L. So that is equals to g, we can say that. So g of e over k is equals to g of e over L, that is equals to g. Therefore, the result B. So this one, F is fixed field of G of E over F. So these are equivalent conditions. So K and L are the fixed field of G of E over L and G of E over K. So that implies K is equals to L. So these are fixed fields. So then we can say that K is equals to L. So G of E over K is equals to G of E over L is equals to G. So K and L are the fixed field of G. So therefore we can say that K is equals to L. So therefore F is 1 function. So G of E over K is equals to G of E over L, that is equals to E. So but here K and L are the fixed fields of G. K and L are the fixed fields of G. Then we can say that K is equals to L. So therefore F is 1 mapping. So F is 1 mapping. So next onto condition. F is onto. So let G be any element of H and K with a fixed field of G. Then G is equals to G of E over K. So by the definition of F, G of E over K is equals to F of K. So F is defined by F of K is equals to G of E over K. F of K is equals to G of E over K. So thus G is equals to F of K. G is equals to F of K, where K is subset is equals to S. K is subset is equals to S because K is belongs to S. We are taking the elements from K and L from S. This one. K and L are belongs to S. So here where K is subset is equals K is belongs to S. So therefore F is onto function. This is nothing but every element in codomain there is a pre-image in domain. So therefore F is onto function. So we are defining a mapping F function S to S is defined by F of K is equals to G of E over K. So we have to verify F is 1 function and F is onto function. So hence there is a 1 correspondence between set of all subfields of E containing F and the set of subgroups of G of E over F. So this one, F is 1 F is on the function. So next, so we are defining mapping. E is a Galois extension statement. E is a Galois extension of F. Let K be a subfield of E containing the mapping K to G of E over K set of a 1 correspondence set. There is a 1 correspondence between set of all subfield of containing subgroups of G of E over K. So ఇప్పటివరకు ఇదే ప్రూవ్ చేస్తున్నాము మనం. So previous steps 1 F is 1 onto is nothing but a set of a 1 correspondency from the set of subgroups of E containing F to the set of all subgroups of G over F is nothing but F is 1 F is onto function. These two conditions, these 3 lines. There is a 1 correspondency from the set of subgroups of E containing F to the subgroups of G of E over F. So this one. Hence, there is a 1 correspondence between set of all subfield of E containing F to the set of subgroups of G of E over F. So we are defining a function, F function S to H. S is nothing but set of all subfields. S is set of all subfields and H is nothing but set of all subgroups. H is set of all subgroups. So there is a 1 correspondence is nothing but 1 and onto function. F is 1 and onto function. So therefore there is a 1 correspondence from set of all subfield of F containing E to the set of all subgroups of G of E over F. So this one. So next, first condition. So this is first condition. K is equals to G E of E G of E over K. K is equals to E G of E over K. So first statement. So this is first one. So we have F subset K subset E. F subset K subset E. So K is nothing but set of all K is set of all subfields. So F subset K subset E, and E is the normal extension of F. So E is the, so this is, so E is the normal extension. So E is extension of set F. E is extension of set F. So F subset K subset to E. So E is the normal extension of F. Therefore, E is normal extension. So therefore, E is normal extension of K also. So this is indicates F subset K subset E is nothing but, so E is the normal extension of F, and this E also normal extension of K is nothing but E is normal extension of F and K. Okay? So E is normal extension of X and F and K. Then by result 2, so K is fixed of G of E over K. So hence K is equals to E of G of E over K. So this is the first condition. So by using this one, second condition. So using this result, so E is fixed separable extension of F. Then the following results are true. E is fixed field of G of E over F. So using this one, we can say that K is equals to E G of E over K. So this is first condition. So next, second condition. For any subgroup H of G of E over F, so H is equals to G of E over EH. For any subgroup H of G of E over F, comma, H is equals to, we have to show that H is equals to G of E over EH. So this is the condition. Second one. For any subgroup H of G of E over F, we have H is equals to G of E over EH, where E is finite separable extension of F. By result 1. So starting assumptions, this is E be the finite separable extension of field F, and let H is less than or is equals to, or H is less than or is equals to G of E over F, then G of E over H is equals to H. Using this result, so directly we can say that for any subgroup H of G over EF, we have H is equals to G of E over EH, where E is the fixed separable extension of F. So by result 1. So next, third result, third statement. So index of E over K equals to, so order of G of E over K. So K over F is nothing but index of G of E over K in G of E over F. So you have to show that this condition. Third one. So E is normal extension of F and K. So therefore, by result 1 to C. So second result, third one. So index of E over F is equals to, so order of G of E over F, and so index of E over K is equals to order of G of E over K. So we have index of E over F is equals to, so here F is subset to K subset to E. So we can write, so E over F can be written as E over K. So these two, E over K and K over F. So E over K and K over F. So E over F is nothing but equals to index of E over K and K over F into K over F. So this is nothing but order of G of E over F. Using this one, index of G of F is equals to order of G of E over F. So order of G of E over F is equals to order of G of E over K into index of K over F. So index of K over F is equals to order of G of E over F divided by order of G of E over K. So therefore, so this can be written as index of G of E over K in G of E over F. So this is the third one. So first three are, these are the first three. Fourth one. So K is normal extension of F if and only G of E over K is normal subgroup of G of E over F. So fourth condition, K is normal extension of F if and only if G of E over K is normal subgroup of G of E over F. Third one, fourth one. 2, 4. To prove 4, we need to follow the result. K is normal extension of F if and only if for each sigma belongs to G of E over F, comma, sigma of K is equals to K. So for to prove, let F bar be algebraic closure of F. So F bar is nothing but algebraic closure field of F, so containing E. We have K is normal extension of F. K is normal extension of F if and only for each embedding K to F bar. So we are defining embedding K to F bar, which every element of F fixed maps K onto K. So suppose K is normal extension of F and so sigma belongs to G of E over F. So sigma is belongs to G of E over F. Then so sigma divides K is an embedding. So this is assumption. Embedding of onto E and hence F bar. Therefore sigma of K is equals to K. So sigma of K is equals to K. So therefore, so this is the first result. So next conversely assume that sigma of K is equals to L. Sigma of K is equals to K for each sigma belongs to G of E over F. So we are defining a function like pi function K to F bar. Pi function K to F bar be an embedding that keeps each and every element of F fixed. Then pi can be extended to an embedding pi star E to F bar, where pi star divides L equals to pi. So since E is a normal extension, we get pi star of L is equals to E. So thus pi star belongs to G of E over F by assumption. So pi star of K is equals to K to pi of K is equals to K. So pi star of K to pi of K is equals to K. So since pi star divides K is equals to pi, so thus if every K tends to F bar, so every mapping pi function K to F bar is an embedding that keeps every element of F is fixed. So this mapping is denotes nothing but every element of F is fixed, so such that pi of K is equals to K. So therefore K is normal extension of F. So this is fourth condition. The last one. If K is normal extension of F, then G of E o K over F is isomorphic to G of E over F divides G of E over K. So suppose K is normal extension of F, then by the above result, sigma of K is equals to K for all sigma belongs to G of E over F. So that implies for all sigma is belongs to G of E over F. So K subset R is equals to K, comma, sigma of K is equals to K. So then for all tau belongs to G of E over K, we have, so we are defining tau of sigma of K is equals to sigma of K. So tau of sigma of K is equals to sigma of K, and so sigma inverse of tau into sigma of K is equals to K for all K belongs to K. So this condition is nothing but sigma inverse tau into sigma. This is nothing but normal subgroup condition. So G, H, G inverse or G inverse H, G. So these two conditions are normal subgroup conditions. So these are belongs to H. So these are belongs to H. Then we can say that H is normal subgroup of G. So G, H, G inverse are, so G inverse H, G. So these two conditions are normal subgroup conditions. So sigma inverse tau into sigma of K is equals to K for all K belongs to K. So sigma inverse tau, sigma is belongs to, so K is nothing but K is equals to G of E over K. G of E over K for all sigma belongs to G of E over F and tau is belongs to G of E over K. So therefore G of E over K is normal subgroup of G of E over F. So this is first part. So next conversely assume that. So conversely assume that. So these are the normal subgroup. So G of E over K is normal subgroup of G of E over F. So that is normal subgroup condition. So sigma inverse tau into sigma is belongs to G of E over K, where sigma is belongs to G of E over F and so tau is belongs to G of E over K. Now we have to prove that. So is normal extension of, so then K belongs to K, sigma inverse tau into sigma of K is equals to K. So tau into sigma of K is equals to sigma of K. So sigma is this one. So multiply both sides, sigma. So tau into sigma of K is equals to sigma into K. So next, tau into sigma of K is equals to sigma of K. Now E is normal extension of F and F subset K subset to E. So therefore then E is normal extension of K. So then K is the fixed field of G of E over K. So we can write this condition. Sigma of K is belongs to K. So sigma of K is equals to K. Sigma is belongs to G of E over F. So hence by the above result, K is normal extension of F. So these are the, so this is fundamental theorem of Galois theory. So this one, fundamental theorem of 16.3.12. So state and prove fundamental theorem of Galois theory. So this is very, very important theorem. So once again statement, so let E be the Galois extension of F. So we can write S is equals to K such that K is subfield of E containing F and T is equals to H such that H is subgroup of G of E over F. So is nothing but F is defined as set of all subfields and T is defined as set of all subgroups. So T is defined as set of all subgroups. Then there is a bijection. So bijection is nothing but 1 and onto. So previously we have to show that F is 1 and onto function. There is a bijection from S to S is nothing but there is a set of correspondency between set of all subfield of F containing F and the set of all subgroups of F. S to T is defined by, so phi of K is equals to G of E over K. So which satisfies the property K1 is subset R is equals to K2 if and only phi of K2 is subgroup of phi of K1. Okay. So next K is normal extension of F if and only phi of K is normal subgroup of G of E over F. Right? If K is normal extension of F, then G of E over F divides G of E over K is isomorphic to G of E over F. So these are the three conditions. The next, solvable by radicals. So let F be a field and R is a positive integer, an element omega belongs to E is called primitive nth root of unity. So this is primitive nth root of unity in F. So we can write omega power n is equals to 1 and omega power m is not is equals to 1. So it's nothing but, so all the elements are less than n is not is equals to 1. So any element is less than n. So omega power that element not is equals to 1. So then we can say that omega is primitive nth root of unity. So and omega power m is not is equals to 1 for any positive integer. So any element is less than n. So this is not possible. Omega power m is not is equals to 1. So we can say that omega is primitive nth root of unity. So note a primitive nth root of unity in C is nothing but complex numbers is e power 2 pi I by n. So e power I theta formula cos theta plus I sin theta. So cos 2 pi by n plus I sin 2 pi by n. So since characteristics of f is equals to 0, so x power n minus 1 has n distinct roots in a splitting field of from cycle group under multiplication. If omega is primitive nth root of unity, then omega power n, where m less than to n and GCD of m comma n is equals to 1 is also primitive nth root of unity. So we know that there is a number pi of n. So we can find the primitive nth roots of unity by using this formula pi of n. So for example, so 1 plus I root 3 by 2 is primitive cubed root of unity for cos 6 pi by 5 plus I sin 6 pi by 5. So is a primitive fifth root of unity. So this is primitive fifth root of unity. Cos 6 pi by 5 plus I sin 6 pi by 5 is a primitive fifth root of unity. So next definition. Let E be a Galois extension of F, then E is called cyclic extension. So E is called cyclic extension of F if G of E over F is cyclic group. So G of E over F is cyclic group, then we can say that E is cyclic extension of F. So next theorem. Suppose F contains a primitive nth root of unity, then the following are equivalent. So first condition is finite cyclic extension of F of degree n. And order of G of E over F is cyclic group, and so order of G of E over F is equals to n. So E is splitting field of irreducible polynomial. E is the splitting field of irreducible polynomial x power n minus b belongs to f of x. So this is the theorem statement. To prove, so our assumption one is true. We have to prove the second condition. A is splitting field of an irreducible polynomial x power n minus b is belongs to f of x. So suppose g of e over f is cyclic group of order n, and so sigma is belongs to g of e over f. Be a generator. So sigma is the generator of cyclic group. So cyclic group is nothing but then there exists at least one generator in a group. Then we can say that G is cyclic group. So our assumption E is a finite cyclic extension of f of order n. Our assumption first one is true. We have to prove that second condition. So E is finite cyclic extension of f of degree n. So G of E over F is cyclic group and order of G of E over F is equals to n. So we have to show that E is splitting field of an irreducible polynomial x power n minus b belongs to F. Our assumption first condition is true. We have to show that second condition. We have to verify second condition. So proof. Suppose G of E over F is cyclic group. So cyclic group is nothing but then there exists at least one generator of order n and sigma is belongs to G of E over F be a generator. Then 1 sigma square up to sigma power n minus 1 are linearly independent over F. So these are the linearly independent sets. So linearly independent set over F. So let omega be the primitive nth root of unity. Let omega be the primitive nth root of unity in F. Now omega not is equals to 0. Omega is not is equals to 0 and 1 plus omega inverse into sigma plus omega power minus 2 into sigma square plus omega power minus n plus 1 into sigma power n minus 1 is a non-zero endomorphism of E as a vector space over F. So these are the linearly independent vectors over F. So these are the linearly independent vectors over F and we are defined as sum 1 plus omega power minus 1 into sigma plus omega power minus 3 into sigma square plus up to omega power minus n plus 1 into sigma power n minus 1 is a non-zero endomorphism of E of a vector space over F. So therefore C is equals to C is equals to I of A. So I is nothing but identity. I of A is nothing but A. So sigma inverse into omega inverse into sigma of A plus up to omega power minus n plus 1 sigma power n minus 1 of A is not is equals to 0. So we are taking sigma. So sigma of C is equals to sigma of A plus. So we are taking sigma on both sides. Sigma of C is equals to sigma of A omega power minus 1. So we are taking sigma on both sides. Sigma is there already. Sigma square of A plus up to sigma power minus n plus 1 into sigma power n minus 1 plus 1. So multiply sigma on both sides. I'm taking sigma on both sides of above equation. So sigma power n of A. So that is equals to, so next taking omega is common on both sides. Omega is common. So here there is no omega. Omega power minus 1 is nothing but multiply and divided by omega. So omega is common. Omega power minus 1 into sigma of A plus. So omega power minus 2 into sigma of A plus up to, so last term I of A. So this is nothing but omega power minus 1 into sigma of A plus omega power minus 3 into sigma of A plus up to I of A is nothing but C. So this one. So this is C. So therefore, sigma of C is equals to omega into C. Sigma of C is equals to omega into C. Since sigma power n is equals to I and omega power n is equals to 1. So because omega is the primitive nth root of unity, so therefore omega power n is equals to 1. Primitive nth root of unity is nothing but omega power n is equals to 1 and sigma power n is equals to I. So in general, so sigma power k of C is equals to omega power k into C for all k is equals to 1 to n minus 1. So in general, sigma power k of c is equals to omega power k into c for all k is equals to 1 to up to n minus 1. So in general term, so this is for k is equals to 1. Sigma of c is equals to omega into c. Hence, sigma of k into c power n. So sigma of k into c power n. Friends, sigma of k into c of c power n is equals to sigma omega power k into c whole power n. So that is nothing but, so this can be written as, omega power n into k into c power n. So but omega power n is primitive nth root of unity, that is equals to 1, and c power n is nothing but c power n. So this total term is 1. Omega power n into whole power k is nothing but 1 into c power n. So sigma power k of c power n is equals to c power n only. So sigma power k into omega power k into c whole power n. So but sigma power omega power n is equals to 1 because primitive omega is the primitive nth root of unity. Omega power n is equals to 1. So that is nothing but c power n. For k is equals to 1 to up to n minus 1. So therefore, c power n is the fixed field of g of e over f. So but f is the, so g of e over f, but f is the fixed field of g of e over f. So then therefore, so c power n is belongs to f. So put b is equals to c power n. So then we are getting x power n minus b. So x power n minus b belongs to f of x, whose roots are c comma c into omega comma c into omega square comma up to c into omega power n minus 1. So these are the roots of x power n minus b belongs to f. However, sigma power k of c is equals to, so c into omega power k. So implies that f of x is the minimal polynomial c over f. So these are the roots c comma c into omega comma up to c into omega power k are also roots of f of x. So but f of x is nothing but x power n minus b. So x power n minus b is divides f of x. So that is f of x divides x power n minus b. So we are getting f of x is equals to x power n in minus b. So the roots of f of x is, c comma c omega comma c omega square up to c into omega power n minus 1. So therefore xn minus b belongs to f of x is irreducible. Also index of f of c over f is equals to n. That is nothing but index of e over f, and f of c substar is equals to f. Hence, E is equals to f of c. So therefore, E is splitting field of x power n minus b over f, and x power n minus b is irreducible polynomial over f. So these are the roots, and the equation x power n minus 1 is divides f of x. So x power n minus b is divides f of x, and the roots c comma c omega square up to c into omega power n minus 1. So and we are defining, so sigma of k of c is equals to c into omega power k. So therefore, so index of e over f is equals to index of f of c over f is equals to n. So this is nothing but degree of the polynomial. So therefore, E is the splitting field of x power n minus b. So and this x power n minus b also irreducible polynomial over f. So this is the first condition. Our assumption is finite cyclic extension of f of degree n, and so g of e over f is a cyclic group of g of e over f is equals to n. Order of g of e over f is equals to n. Our assumption. So we have to show that E splitting field of an irreducible polynomial x power n minus b is belongs to f of x. So this is first case. So next, second one, our assumption, second one is true. We have to show that first one. So it's nothing but E splitting field of an irreducible polynomial x power n minus b belongs to f of x. Then we have to show that E is finite cyclic extension of f of order of degree n. So G of E over F is cyclic group and order of G of E over F is equals to n. The second one. Let C belongs to E be a root of x power n minus b belongs to f of x. So that is nothing but b is equals to c power n. So c is the root of equation x power n minus b is nothing but c power n minus b is equals to 0. So b is equals to c power n. So b is equals to c power n. Clearly, then c comma c omega comma c omega square comma up to c into omega power n minus 1 are the n distinct roots of x power n minus b. So these are the distinct roots. So previously we have to show that these are the roots of the here. So c comma c omega square c omega power n minus 1 are the distinct roots of x power n minus 1. Here also c comma c omega square come up to c omega power n minus 1 are the distinct roots of x power n minus b. So where omega belongs here is a primitive nth root of unity. Thus x power n minus b is separable irreducible polynomial. Our assumption x power n minus b is separable and irreducible splitting field and irreducible polynomial. So this separable field and irreducible polynomials. Hence, E is equals to f of c is Galois extension of f. E is equals to f of c is the Galois extension of f. So for each sigma belongs to g of E over f. So each sigma belongs to g of E over f is defined by x of sigma is equals to k belongs to z. So sigma of c is equals to omega power k into c. So sigma of c is equals to omega power k into c. So then sigma x of sigma is not is equals to 0 because sigma of c is also root of x power n minus b. So this is not is equal to 0 because x power c sigma of c is a root of x power n minus b. So moreover, for any k belongs to x of sigma, so k belongs to x of sigma. So sigma of x of sigma is equals to k bar belongs to z by n. For omega power k into c is equals to omega power I into k if and only if k is equals to j. K is equals to j mod n. Further, sigma comma tau belongs to g of e over a and sigma of c is equals to sigma power k into c, omega power k into c, and tau of c is equals to omega power j into c. So we are defining two functions. So tau and sigma. So tau and sigma belongs to g of e over f. So these are defined by tau of c is equals to omega power j into c. Sigma of c is equals to omega power k into c. So multiply sigma into tau of c is equals to sigma of tau of c is nothing but omega power j into c. So omega power j is constant, omega power j into sigma of c. So sigma of c is nothing but omega power k into c. So omega power k plus j into c. So therefore, so x of sigma into t is equals to x of sigma plus x of t. So this can be written as x of sigma into tau is equals to x of sigma plus x of tau, where the sum of two the sum of the right. So this is denotes nothing but binary operation, additive binary operation, additive group. So x of tau into sigma is equals to x of tau plus x of sigma. So this is nothing but additive group of z by l. So finally x of sigma is equal to 0. Then sigma of c is equals to c. So sigma is equals to identity on E because E is equals to f of c. So consequently, x is an isomorphism of g of E over f onto a subgroup of additive group z by n. So this is subgroup of additive group z by n. Also index of E over f is equals to degree of the minimal polynomial c of E over f, that is nothing but n. So degree of given polynomial x power n minus b. So therefore, so degree of E over f or degree of g of E over f is equals to n. So because g of E over f is isomorphic to subgroup z by n, it is follows that so g of E over f is isomorphic to z by n. So this is the theorem. So this is the very important theorem, fundamental theorem of Galois theory. So this one, fundamental theorem of Galois theory, confirm question. So these are solvable groups. So in the solvable groups, so only one theorem important last. In solvable groups, so this is the important theorem. So next class, solvable by radicals. So 17.5, polynomials solvable by radicals. You have to learn this question. This is very important question. Fundamental statement question. Statement fundamental theorem of Galois theory. 8th question in your question paper.
సార్ నోట్స్ షేర్ చేయండి సార్.
ఆ నోట్స్ నేను గ్రూప్ లో లేనమ్మా నేను.
సార్ నెంబర్ ఇవ్వండి సార్.
నేను జాయిన్ అవుతాను, మెసేజ్ పెట్టారు కదమ్మా గ్రూప్ లో.
వాట్ సార్?
మీరు గ్రూప్ లో మెసేజ్ లింక్ పంపించారా ప్లీజ్ జాయిన్ అని చెప్పేసి, జాయిన్ కావట్లేదు అది.
సార్ నాకు సెండ్ చేయండి సార్, నేను గ్రూప్ లో సెండ్ చేస్తాను.
నేను ఇంట్లో మెసేజ్ చేస్తాను చూడండి అమ్మా, నేను గ్రూప్ ఇప్పుడు మెసేజ్ చేస్తాను చూడండి ఇక్కడ.
ఓకే సార్.
నేను చాట్ లో పెట్టాను చూడండి అమ్మా.
కావాలా ఎతుల పాణిపి
We'll see in next class.
ఓకే సార్, థ్యాంక్ యూ.
థ్యాంక్ యూ సార్.